Welcome to the Explainer. You know how your phone can recognize your face or how a self-driving car sees the road? Well, the magic behind it is something called a convolutional neural network, or CNN. Today, we're going to break down exactly how they taught computers to see. So where did this all begin? Well, it all kicked off with what seems like a pretty simple question, right? How do you actually teach a computer to know what a cat is? The journey to answer that question, though, completely changed everything we thought we knew about artificial intelligence. For a long time, the old way was, well, let's just say it was clumsy. We'd take an image, unroll every single pixel into one giant flat line, and just feed it to the AI. But think about it. That destroys all the important spatial info. You lose the fact that a cat's eye is next to its nose. The big breakthrough with CNNs was to stop doing that and start treating an image just like we do, as a 2D grid, where the relationships between pixels are absolutely everything. And at the very heart of this new way of seeing is a single powerful idea. It's a mathematical operation called the convolution. Seriously, this one concept is the key to how computers finally started to make sense of the visual world. So instead of trying to understand the whole cat picture all at once, a CNN uses these things called filters. The best way to think about a filter is to imagine it's a tiny little spotlight. And this spotlight just slides across the image looking for one very, very specific thing, like a sharp vertical edge, or a patch of fuzzy texture, or maybe the curve of an ear. And what is this filter, this little spotlight? It's actually just a small grid of numbers, also called a kernel. That's it. The entire learning process for a CNN is really just about the network figuring out the perfect set of numbers for thousands of these filters, turning each one into a master detector for a tiny piece of the puzzle, whether it's cat whiskers or car wheels. Okay, so the network has its spotlight. Now it has to decide how to move that spotlight across the image. And that's where stride comes in. It's basically the step size. If you use a small stride, you're doing a really careful pixel-by-pixel scan. A larger stride lets the filter jump across the image way faster, but you do risk missing some of the finer details. And what about the stuff at the very edge of the picture? You don't want to miss an important clue just because it's right at the border, right? Well, that's what padding is for. It's kind of like adding a blank frame of zeros all around the image. This lets our little filter process the edges just as thoroughly as it does the center. Now this right here is the idea that makes CNNs so incredibly, unbelievably efficient. It's called parameter sharing. Think about it. Instead of learning one detector for a cat's ear on the left side of the photo and a completely separate one for an ear on the right, a CNN just learns a single ear detector filter and uses that same filter across the entire picture. This one clever trick just massively reduces the amount of stuff the network has to learn. It's a total game changer. So, with these basic building blocks in their toolbox, the convolution, the filter, the stride, researchers basically kicked off a race to build bigger, deeper, and way smarter networks that could tackle some seriously complex visual challenges. And this timeline tells an amazing story of just explosive progress. I mean, it started small back in the 90s with LeNet, which was just proving the concept on handwritten numbers. But the real big bang was in 2012 with AlexNet. It didn't just win a competition, it absolutely crushed it and kicked off the entire modern deep learning era. From there, it was just off to the races. VGG proved that just going deeper could work, until ResNet came along with a brilliant hack that let networks get truly massively deep. But as people were building these deeper and deeper networks, they hit this really bizarre, frustrating wall. The networks would get better and better and better, and then, suddenly, you'd add one more layer and performance would actually get worse. This baffling thing was called the degradation problem, and it seemed to put a hard ceiling on how powerful our models could ever get. Then, the team behind a new model called ResNet had this flash of genius. They realized it's actually really hard for a deep layer to learn to do nothing, to just pass the information through unchanged, even if that's the best move. So they flipped the question. They thought, what if we make doing nothing the super easy default path? What if we only ask each layer to learn the tiny difference from the layer that came before it? And their solution was just elegance itself. It's called this skip connection. The input signal doesn't just go through the processing layers. It also gets to take a shortcut, a skip lane, right around them, and then it gets added back in at the end. This simple addition creates an information superhighway that makes it effortless for the network to just let the signal pass right through. It solved the degradation problem practically overnight and let us build networks that are hundreds of layers deep. So
These incredibly deep, powerful networks set the stage for what is, I would argue, the most important, most practical technique in all of computer vision today: transfer learning.
And it all starts right here with a gigantic public dataset called ImageNet. We're talking over 1 million labeled images across 1,000 different categories. For years, the entire community has trained enormous models on this dataset, essentially teaching them a foundational, general-purpose understanding of what the visual world looks like. What are edges? What are textures? What are shapes? What are objects?
And this leads us to transfer learning. The idea is brilliant in its simplicity. Why would you ever start from scratch? Instead of trying to teach a new model about vision from ground zero, you just take one of these models that's already been pre-trained on ImageNet. You give it a massive head start. It already knows what an eye is, what fur looks like. All you have to do is fine-tune it on your very specific problem. And the playbook for this is so simple, but it's unbelievably powerful. Somebody else does all the heavy lifting. They spend weeks and a ton of compute power pre-training a giant model. Then you just download that model and you continue its training. You fine-tune it on your own much smaller data set. Maybe you've got a few thousand pictures of specific bird species or a set of medical scans. It's that easy.
This whole idea has become the absolute golden rule of modern computer vision. Never train from scratch if you can possibly avoid it. Transfer learning isn't just a nice-to-have, it's what makes state-of-the-art AI accessible to pretty much everyone, saving just incredible amounts of data, time, and money.
But of course, technology never, ever stands still. The convolution has been the undisputed king for a decade, but the next evolution in computer vision is already here, and it's actually coming from a totally different field. So say hello to the Vision Transformer. It's an idea borrowed straight from the world of language models like GPT, and it works in a completely different way. You see, a CNN is like a person looking at a photo through a tiny magnifying glass, focusing on all the local details first. A Vision Transformer is more like someone stepping way back to see the entire painting at once, understanding the global picture, the relationships between all the parts from the very beginning. This makes them incredibly powerful, but there's a catch. They are even more data-hungry than CNNs, which leaves us with a final big thought. In just about a decade, we've gone from struggling to identify a handwritten number to giving machines a sense of sight that can, in many cases, actually rival our own. We fundamentally changed the world with this technology. So the big question is, what happens when we give them another sense?